Okay, in this podcast we're going to talk about the ideal gas law. This is a law that assumes that gas molecules are really far apart from each other and moving pretty quickly so that they have no interaction whatsoever. It's kind of based on that kinetic molecular theory of gases that we learned earlier. First thing we're going to talk about is Avogadro's principle. This says that equal volumes of gases at the same temperature and pressure have the same number of molecules. That's kind of a long sentence, so let me help explain that a little bit. Let's take this example right here. We have two balloons. One's got helium on the left, and the one on the right is carbon dioxide. Let's put these things at equal temperature and pressure, 273 Kelvin and 1 atmosphere. What you'll notice is Avogadro said that they are the equal volumes. We'll go ahead and assume those balloons are the exact same size. That if they are at equal temperature and equal pressure, they should have the same number of molecules. So let's see what they look like. So you can see that helium's molecules are much smaller than carbon dioxide, but the number of molecules in each balloon is the exact same. So that's what Avogadro's principle suggests, that if these two are at equal volume and equal temperature and equal pressure, they're going to have the same number of molecules as well. So what you can see is that the carbon dioxide balloon would weigh 11 times more than the helium balloon, because they have the same number of particles, but the carbon dioxide particles are much, much larger. What Avogadro found out was that 1 mole of gas at 273 Kelvin and 1 atmosphere had a volume of 22.4 liters. It didn't matter which gas it was, it would be any gas. It's just that maybe one gas might weigh more than another, but the same number of molecules are present within that situation. We refer to 273 Kelvin and 1 atmosphere as standard temperature and pressure, abbreviated STP. You'll notice that I've written 1 mole of gas at 273 Kelvin and 1 atmosphere has a volume of 22.4 liters. So the 4 variables you need to consider whenever you're talking about a gas in the ideal gas law: amount of gas, temperature of the gas, pressure of the gas, and of course the volume of the gas. You need to make sure these 4 variables are taken into consideration whenever you are describing the ideal gas law. Using Avogadro's law and experimental data, an equation was developed to show that relationship. We call it PV equals nRT. Pressure times volume equals moles times this R times temperature. The R represents the ideal gas law constant and was discovered experimentally. In order to figure out the value of R, we're going to go ahead and take 1 mole of gas at standard temperature and pressure, knowing that it takes up a volume of 22.4. So if I show you the equation here, P, pressure, is equal to 1 atmosphere, V, volume, is equal to 22.4 liters, N, moles, is equal to 1 mole, the R is what we're trying to solve for, and the temperature is 273 Kelvin. If we solve for R there, we get 0.0821. Notice that our pressure was in atmospheres in order to get this R value. Had our pressure been in kilopascals, you can see that we're not going to get the exact same R value. If we solve for R value here, we get 8.31. So if your pressure is in atmospheres, the R value is 0.0821. If your pressure is in kilopascals, it's 8.31. You could also do this for other pressures as well, but these are the 2 you should know. Let's go through an example here. What mass of nitrogen gas is contained in a container with a volume of 890 milliliters at 21 degrees Celsius and a partial pressure of 85.0 kilopascals? So I'm going to go ahead and show you how the equation is set up here, and we'll go through it together. Here's the equation of PV equals nRT. Notice I put my pressure in kPa. That led us to have the R value of 8.31. Notice I did not use the 0.0821 because our pressure is in kPa. Secondly, the volume has to be in liters. 890 milliliters is equal to 0.890 liters. Lastly, the temperature has to be in Kelvin in order for this equation to work. 21 degrees Celsius plus 273 equals 294 Kelvin. So when I solve for this, I'm going to get 0.0310 moles of nitrogen gas. Notice that nitrogen gas is diatomic, and we're going to go ahead and figure out what mass it is. In order to get our moles of nitrogen into grams of nitrogen, we multiply by the molar mass. In this case, we take the 0.0310 moles multiplied times 28 grams per mole, and we get 0.868 grams of nitrogen gas. Keep in mind that the pressure was in kilopascals, and we had to use 8.31 for our R value in this equation. Had it been in atmospheres, we would have put the pressure in atmospheres, and the R value would have been 0.0821.